So for now, we'll just move on to the next one. So in BiDS CDSE Jupyter, the last one, number 3, deforestation time series with xarray. And you can open that notebook. Full screen this. And so what we want to do now, we have worked with pandas now, which is kind of tabular data. And now we want to see how all of this data workflows fit into xarray. Maybe the same question as before. Who here has worked with xarray before? 1, 2, maybe. Not so many. Okay, so xarray basically is probably a lot more have worked with the netcdf data before. And xarray is the way in Python to work with multi-dimensional data. So we only worked with tabular data before, and xarray allows you to very efficiently work with multi-dimensional data. So in our case, it's x, y, time, and different bands, so 4 dimensions mostly. And it's very based in the netcdf world, but it offers a lot, very good compute capabilities and time series analysis capabilities, which we want to leverage now to do some simple deforestation monitoring based on a time series. So for deforestation monitoring, we will use Sentinel-2 again, and we just want to see over a basic thresholding algorithm or classification. We want to classify forest loss over the different years. So first of all, change the kernel. Don't forget that, because we have to install a few packages here, the libraries here. So we run this cell. In this case, we use Dust, but not massively, yes. And this should install all of the remaining packages that are necessary, which we can then import. Here again, you don't have to run this if you've already configured your configuration. You can just change in here in the shconfig to CDSE or whichever name you saved your configuration in, and run this, and that should work for you. So in our case, we have an area of interest. We'll look at the Harz Mountains in Germany, which have had a lot of forest loss over the last years. You can also change the bounding box to some area that interests you if you want to, but it's not necessary. We can just quickly see the area. We can explore the area of interest in the Copernicus browser as well. There's a link in the notebook. Let me get out of. I don't know why it doesn't load. Ah, yeah. We need to add the HTTPS, unfortunately. I forgot that. And so here we can look at the data in the Copernicus browser. So this is our area. This is the Harz mountain range in northern Germany or middle of Germany. And we'll look at the deforestation in this kind of area. So our resolution that we're doing this in is 100 by 100 meters. You could also do it in 20 by 20 meters, but just in the interest of keeping the queries quite quick, we're doing it with 100 meters. But if you want, and you want to push the infrastructure a bit more, please go for 20 by 20. So this we can skip for now. It will work later. And what we now want to do is, we already did a kind of more simple mosaic for Sentinel 5P. And we want to do the same thing with Sentinel-2 now as well in an eval script. And in this case, we want to do a cloud-free mosaic, which requires one more step than the one we did for Sentinel 5P. In this case, in the setup function, we want to return band 8, 4, 3, 2, and the scene classification. Band 4, 3, and 2 are just for a true color visualization. We don't need them necessarily, just to have a look at the data. All we really need, because we want to do this with NDVI, is band 8 and band 4. Then the output is 5 bands. We want 4, 3, and 2, and 8, and the NDVI, that's 5 in total. Then output type or sample type is integer, and mosaicing is orbit because we again want to look at the entire time series to construct the mosaic. So let's look at the evaluate pixel function. This is a bit more complicated, but it should be familiar. Parts of it should be very familiar to you. So first of all, we again filter out all of the values that are cloudy. So in this case, we are using this validate function, which we can look at down below. And the validate function basically takes the SCL band and then checks if the value is in one of those defined values that we define as invalid. So no data, cloud shadow, clouds, thin cirrus, and so on. And we filter all of those values out. Once we do this, if there's still any data left, we can keep going and get the first quartile value of all of the remaining values. So first quartile, because clouds tend to be very bright, and the first quartile will give us a bit of a darker pixel than the mean value, because it's the first quartile value. So this further reduces the chance that by accident we still get a cloud, because we are not taking the mean, we're taking a bit of a darker pixel, but it's the same for all of the pixels, just like a bit darker pixel. Then we also calculate the NDVI over here with the cloudless values that we just constructed. So band 8 minus band 4 divided by band 8 plus band 4. And to return all of this data, we also apply a scale factor. If you've worked with Sentinel-2 data, like raw Sentinel-2 data before, this is probably familiar to you. The scale factor basically allows you to save decimal data, floating point data, as an integer, which reduces the file size by quite a lot. It also reduces the amounts of processing units that you will spend on it. So in this case, we just multiply it by 10,000. And later then we have to divide it again by 10,000 just to get the actual values back. And that's what we're doing. So let's run the eval script. And what we do is to construct the time series. We want to do a mosaic, a cloudless or cloud-free mosaic for 3 months for a range of years. So from 2018 to 2023. We pick 3 months, the same 3 months for each of those years. So in our case, we pick June to September and construct this request with the bounding box, our resolution that we picked, Sentinel-2 input data, our eval script. And the only thing changes, depending on the year, is the time interval. And if we run this, and for all of the years that we select, so 2018 to 2023, we then get one request for each year, where the only difference basically is the time interval that we picked. So for each year, it will construct a cloud-free mosaic for our specified months. We can download all of this with this download client. Again, it will do it in parallel, or it should do it in parallel. For me, it was quite quick. Maybe it was run before, I don't know. If the same request was run before, it will get the cached version out, just to make it quicker. I don't know how it is for you, but yeah. Nice. Yeah. Yes. Statistical API at the moment, I mean, the service is still quite young. We're figuring out while we go. You can expect improvements in the future, based on your feedback as well. At the end, we'll have a questionnaire for you. I think you can, yeah. So now one thing, the data is saved in a format where we don't know from which year it is. Right now, we still know which request belongs to which year, so we just rename all of the files to the years that they come from. And that's just happening here. We rename to the year. And if we look into our data folder, we can see all of the TIFFs that our request just sent to us. So 2018 to 2023, each year, one cloud-free TIFF. And now the next step, because we want to work with xarray and this very powerful tool, is to actually get this data into xarray. And because xarray mainly is built on netcdf files, which we don't have, we just have a bunch of TIFF files that have like an implicit date assigned to them, we have to tell xarray from which year each TIFF is from. And this is just a helper function to do that. So it gets the input path of our TIFF. The stem is just the file name without the extension. And then we assign the dimension year to the year we just passed from the file name. So if we run this and the next file, or the next cell, where we get all of the TIFFs that we just downloaded with xarray open multi-file dataset and give all of the paths to the TIFFs, this preprocess function is the one we just defined for adding the time dimension. And then we rename all of the bands, because they're not very descriptive at the moment, to the actual values of the bands that we requested. We'll get a bunch of warnings, which we can ignore. That's just because of the structure of the TIFF files that we got. And then if we look at the xarray dataset, we can see what we got. We have up here the dimensions, so 6 years, x coordinate 105 pixels, y coordinate 98 pixels. In the data variables, RGB and NDVI. That's all we have right now, and if we can also plot this, so we have for 2018, for example, we can do a true color plot, which will look like this. Still quite green. Now you can also change that and just change the plot here. For example, if we go to the other extreme, 2023, we can immediately see quite a big difference. We can also plot our NDVI time series. So with our dataset.ndvi, just plotting the NDVI, where the column is defined by the year. And this is the NDVI over the years. So we can see mainly in the northern parts, if we compare between 2018 and 2022, for example, that the NDVI is reduced quite a bit, which points towards forest loss. All right. Is everyone still following, running well? Nice, perfect. So the next step is doing a classification, a forest classification. In our case, it's very, very simple. We'll just do a thresholding classification. So we just say everything where the NDVI is bigger than a certain value, that's a forest. It's not the best classification. It's just basically to show the overall way to handle data. You won't win any, you won't be able to publish this, you won't be able to do much with it. It will just give a rough overview of loss of NDVI, or basically active plant matter over the time. So in our case, we define everything greater than 0.7 NDVI as a forest. So in this case, we define a new data variable in our dataset called forest, and we assign to it this mask. So in this pixel, or in this mask, for each time step, we will have a binary mask of 0 and 1, forest and non-forest, based on our classification. So if we run this, and we can also now do first statistics on it. For example, we can sum up all of the forest pixels per time step and see, okay, how big was the forest area for each time step. That's what we're doing here. So with the data set, we select forest and then sum up along the x and y coordinates. So year stays the same. We will keep the year dimension, but x and y coordinate, we sum up along that. So for each year, we get just one value out, which is the sum of forest pixels. We convert that to the square kilometers, which is based on the resolution we picked, and we can plot that. So this is what it looks like based on 0. We start out up here at around 80, 90 square kilometers, and the lowest point is at around just about above 60 square kilometers for forest area. You can also, you could play around with this a bit and maybe change the threshold value. If you put in, for example, 0, let's be extreme 0.9, you can see how this changes. So we expect the forest cover to decrease quite a bit because we have higher standards of what a forest should be now, which is definitely the case, only 6 square kilometers. So we'll stick with the 0.7 that we looked at earlier and keep going with it. So the next step that we want to do is we want to make change maps per year. So we want to see from one year to another which pixels were lost, where was forest lost and where was forest gained. To do that, we just take the difference of the forest cover mask from time step to time step. And that will give us kind of a classification of if it was lost, if everything stayed the same, or if there was forest gained. So if in 2019, for example, it was classified as no forest, and in 2018, it's still no forest, 0 minus 0 is 0. Same for if both are 1, it's no change, it's still 0. If in 2019 it was forest, and beforehand it was no forest, 1 minus 0 is 1, and same for the other one, 0, so no forest to forest, or other way around, forest to no forest, you get -1. And this is just done by taking the difference between two directly adjacent time steps. And if we look into here, this happens right here. So we select the forest data variable, convert it to an integer, and then take the difference. So .diff will take the difference between two time steps, or at least in this case, because we are saying along the year dimension, we want to take the difference. It will take the difference between those two time steps. And label upper just means it will give 2019 minus 2018, not the other way around, not 2018 minus 2019, because that wouldn't give us this kind of mapping of the values. And we assign all of that to a new data variable, which is change. So if you plot all of this, so this is the plot year 2022, we can look at the forest change map and see all of the pixels where forest was lost between 2021 and 2022. And we also have some pixels which are signified in blue here, which are forest gain, which is probably classification error. But we'll come to validation or comparison to other data a bit later. So we can also plot that, the forest loss per year, as a cumulative function, basically, where we select from the change data variable, we select everything which was lost, so -1. And then, same as before, we sum that up along the x and y coordinate and can plot it over the years. As a, I mean, a bit before we do the cumulative sum, so it will just increase, so forest loss increases year over year. And this is what it looks like, where we can see a sharp increase like from 2022 to 2021. And from 2021 to 2022, it's like the biggest increase in forest loss. And then to 23, it slows down a bit again. Yeah. Now let's do a small experiment about validation, because as I said before, it's a very simple classification that we're doing. And now it would be interesting to compare it to very well respected data that we have. And the most widely used data for forest loss is the Hansen data from Global Forest Watch. Global Forest Change, sorry. And we can download this in this cell. This will just download the data. If you've changed the area of interest, this might not work because you get it in tiles. It doesn't work with our nice Sentinel Hub requests, where you can just get exactly the same area for exactly the same and exactly the same everything, just for a different data set. So here you'd have to actually change the tile you would get. But in any case, we can then load this data and have a look at it. So ground truth is opened with xarray. We clip it to our bounding box that we defined earlier, reproject it to the same bounding box, select the first band, and just fill the no data with 0, just to not have to deal with no data. And this is kind of the data that we get. So it's quite different to the data we looked at before, or the data we constructed, because it's just a single file. It only tells you the day or the year where forest was first detected as lost. So it's not multiple files, one for each year. As we just constructed it, it's a bit different, just one file, and it's encoded as like the 2 last digits is the year when it was first detected as lost data. So we also have to change our data to be more like that data if we want to compare the two. Okay, so first of all, we can load this data into our already available data set, and this is kind of the magic function in xarray to get data sets to be compatible with each other. It's called interpolate. So interpolate one data set to look like the other data set. So this will change the resolution. It will change all of the coordinates to match exactly the one of the data sets that you want it to match. And you can choose an interpolation method. In this case, we just pick nearest. And we want to interpret it like our data set, because our data set has 100 by 100 meter resolution, and our comparison data set is 30 by 30 meters. So if we do that, that works without any effort. And if we look at our data set now, we see all the same dimensions, all of the data variables that we added, so our forest mask, our change mask, and then over here we have the ground truth data. And if we look closely, all of the other data sets have 3 dimensions, so year, y, and x, and ground truth is only available with y and x because it doesn't have a year. All right, so let's change our data to look more like the data of our comparison. And to do that, we first take the last 2 digits of the year the data is from for our change maps. So divide it by 100 and take the remainder. Then we multiply that everywhere where the change map is -1. So now we will have, for each year, a map where everything that was lost that year has the value of that year. So if something was lost in 2022, we have a big raster where everything where it was lost says 2022, everything else says 0. And then because of our classification, it could switch back and forth, right? It could go Forest, no forest, and then forest again, and no forest again, for example. And so we only want to take the first time that happens. So we go from 2018 to 2023, and the first value that is not 0, we take that and write it to our raster. That's what happens here, basically. The first one that's not equal to 0 along the 0 axis should be written out. And that is then written to a new data set or data variable called lost year. If we plot that, this is what our classification looks like. So here we also have the years, the different years when forest was detected as lost. If we compare that now to the Hansen data, it looks quite a bit different, but there are similar patterns. So with the Hansen data, you have this kind of north-south divide, which we also have, where here all of no forest loss was detected. We have this spot in the middle where less forest loss was detected, also like some areas around the top. So it is definitely not the same, and it can't be, because if it was the same, then Hansen wouldn't have to, like, that wouldn't be worth the publication. But it's good to compare now. And we can do a very simple validation where you just look at the area of forest loss and no forest loss, and if that matches up. We can do a confusion matrix and count up everywhere where in our map it's forest lost, and in our comparison map it's also forest lost, and sum up all of that. Then the same for the no forest lost and no forest lost, and do the same with the errors. So our comparison says there was loss, but we said there was no loss. And the other way around as well. The comparison says there was no loss, and we said there was loss. And then from that we can calculate the overall accuracy. So that's what happens here. We have the score, accuracy score, where we just take everything larger than 18. So because we only start in 2018 and the Hansen dataset already starts in 2001. For our lost year and for our ground truth data, we do the same, everything above 18. And we can calculate the accuracy compared to our comparison dataset. And just a word on that classification metric. So we get out 0.77. So 0.5 would be, it's completely random. Our classification doesn't do anything compared to what the Hansen dataset says. 1 would be it matches exactly. 0.77 is so-so, basically, which we can expect from what we've done so far. And also just a note on that, because this isn't ground truth data, no one went actually down to the Harz Mountains and looked at like the forest stands and said, okay, this is that. The Hansen data is also based on satellite data, so it also has its classification errors, which we can't take into account here. So this is not like an accuracy of our data set in total, like compared to the actual real world. It's a classification error against an already classified data set. So our data set could be better, but it's probably not. So yeah, just something to keep in mind here. So 0.77, so-so, but kind of good enough for what we're doing here. So yeah, this kind of showed how to do a simple time series analysis and monitoring, and doing all of that in xarray and using the cloud tools to get mosaics very quickly. I mean, you've seen how quickly you could do those without having to download much data, getting it into your analysis very quickly, and doing a very simple analysis just right off the bat without having to do much of data downloading, data cleaning, or anything else. That's mainly what I wanted to show here. And that's all I have for you today, or so far. And I think Andras will take over from here. And if there's any questions, please don't hesitate to ask.